Okay, so this is my video for standards 2.2 and 2.3. I chose problems 2.13 and 2.17. I kind of forget which one goes with which standard, but I know one of them satisfies each standard, so I'll show you 2.13 first. So we want to show that the commutator of our SI and SJ spin operators equals SK when we're looking at the SX, SY, and SZ spin operators. So the way we do this is we just compute them all explicitly, brute force it out. So first we'll do the SXSY one first. So first we write out what it means to take the commutator of two operators, and then from there it's just straight up computation with matrix, except for this one little trick right here where you pull out the I out of the 2 by 2 and rewrite h bar squared over 2 as h times h bar times h bar over 2, and then you can see we have the SZ operator right here. This should be a -1 right here. I had a typo in my LaTeX. So we'll do the SY-SZ1 next, which is an exactly analogous calculation to the one above. Again, write out what it means to take the commutator, crunch through the matrix computation, and then do the same trick as before where we pull out the I and rewrite h bar squared over 2. And then you can see right here that we have the SX operator. The SX-SZ1 is fairly similar. There's one more little trick, but it's really not too complicated. So again, just write out what it means to take the commutator, crunch through the algebra a little bit, and then we get to this step right here, and we're feeling kind of worried because we know from the pattern, at least that we have before, that we're going to want to get out the SY operator times I and h bar, and at first glance it doesn't look like there's going to be any way to get an I or the SY operator, which also has I's in it, until you realize that we can rewrite -1 and 1 in terms of I. So -1 is just I squared and 1 is -I squared. Then we can just do the same trick as we were doing before by pulling out one I and rewriting the h bar squared over 2, and then we can see that this is the SY commutator. Oops, and I have another typo, so that should be the SY one right there. Just forgot to change the subscript. So yeah, that's all there is for problem 2.13. So let's move on to 2.17. So in 2.17, they give us this state vector psi, written in the SZ basis, and it's a spin 1 system this time, so we have 3 dimensions. And in part A, they ask us to calculate the probability of measuring each possible state in a spin 1 system from this if we measured this psi. So since this state vector is written with respect to the Z basis, the probability of measuring it in the ith state is just the modulus squared of the ith component. So then the probabilities are easily seen to be 1 over 30, 4 over 30, and 25 over 30 for the states 1, 0, and -1 respectively. And then it asks us to compute the expectation value for the SZ operator. And again, this is fairly simple because we have the probabilities for each state explicitly. So the expectation value is just the sum from -1 to 1 of I, H, and then the ith probability. So that's just weighting each outcome by the probability of obtaining it, which we calculated above, and we end up with -24 over 30 h bar. So in part B, they asked us to calculate the expectation value for the SX operator, and it's a little trickier because since the state isn't written with respect to the SX basis, it would be a real pain to compute all the probabilities explicitly. Luckily, we have a little shortcut around that because we've shown in class that the expectation value for an arbitrary operator is just, you just take the inner product with the operator sandwiched in between the brown and the cat. I think that's called. So we keep going and just carry out that computation. So I've pulled out all the constants from in front of the vectors and the operator here. So that's just out here. And then this is, I did this matrix multiplication in Mathematica, and this should be 2h bar 15 over root 2. So that's it for problem 17.